Hello everyone. Yes, in the last video we talked about generalized impulse response functions, and we drew our conclusion over there. We have drawn the conclusion. Now before we move on, we are at the end of the chapter, and very important topic, bringing an end to that, and we will see some applications today. However, before that, just one important thing I want to talk about. You see, impulse responses of a threshold autoregression, where we have seen this example. Okay, and for this one important point is, for comparison, the analytical IR of an AR1 model are given by setting phi2 equals 0. Okay, and reversing the shock from positive to negative, we see our asymmetrical impulse responses for the TAR model, with the impulse responses decaying at a relative faster rate for the negative shock. So in the second problem that we solved, we just put the second element to 0, and when we change the sign of our shocks, we see that the symmetrical impulse response line decays at a faster rate for the new negative shock. In contrast, a linear AR model impulse responses exhibit symmetry. In case of a linear model, the rate of decay is same for positive or negative shock. So for a asymmetrical impulse response function, or a non-linear, in case of a non-linear threshold model, the impulse response function decays faster for the negative shock, whereas the speed of decay remains same for the linear AR model. This is very important to remember. Very crucial, differentiation between a non-linear and linear impulse response function, or a generalized and a non-generalized impulse response function. Now, the construction of the impulse responses presented in this example was obtained by averaging across all of the shocks. An alternative refinement is to average across histories, that we also did. If you remember in the problem, where the initial condition is a particular sign. So initializing with a sign, we not only averaged across different horizons, we also averaged across the lags. Finally, was the approach is presented for single equation nonlinear time series model. It generalizes to a multivariate nonlinear time series model. So when we present the system with a one nonlinear time series model, or a vector, it gives us a multivariate time series model, or else the impulse response function gives back a matrix to us, where, as we can recall, by the rows we have the lags, by the columns we have the horizons. And for example, Coop, Pessaran and Potter provides an example based on a bivariate TAR model of output and unemployment. We exactly solve this problem. So let's move on to some applications, then we'll see some of their applications very quickly. In this application, a multiple equilibrium model of unemployment, in this application an Elster model of the United States monthly unemployment rate is specified and estimated. So 19.5, right? Let me see. Okay, sorry, this is not 19.5. Given in figure 19.5, monthly unemployment rate given in figure 19.5, right? Okay, let's just look for it. 19.5. So this is the 19.5, the figure 19.5, where the United States monthly aggregate unemployment rate is given to us. So let's get back to our problem, which was, I think, something after, yeah. So figure 19.5 is specified. First it is specified, then it is estimated. Following following Skalin and Terasvirta, a two-regime error correction model of the change of the unemployment rate is specified, right? So two region, the first region is mu1 alpha 1 yt minus 1, the second region is mu2 alpha 2 yt minus 1 is the non-linear region. Okay, it's the non-linear parameter, and this is the objective function within the non-linear parameter, where structural residual is an IIT disturbance term. The weighing function in this case is exponential of minus gamma, then the 12 season up until 12 season lagged minus c divided by s. So where is the lagged annual change, delta W 12 yt minus 1 is the lagged annual change in the unemployment rate, c is the threshold, and s is scaling factor equal to the sample standard deviation. So scaling factor is basically the sample standard deviation of the 12 annual lag. So we rewrite this equation for the weighing function, and we have mu1, well, taking alpha 1 as common, take alpha 1 outside of the bracket, we have mu1 alpha 1 yt minus 1 alpha 2 mu2 by alpha 2 yt minus 1. Express the model, this expresses the model in an error correction form. Okay, so we have this model expressed in an error correction form, where the parameters alpha 1 and alpha 2 represent the error correction parameters. Okay, so this has been discussed in exactly the earlier chapter in time series, especially in co-integration. Not necessary to revisit, just focus on the current one. So we have alpha 1 and alpha 2 representing error correction parameters. As a result of nonlinear specification, two unemployment rates satisfy the equilibrium condition. These two unemployment rates basically satisfying the equilibrium condition, delta yt equals 0. So in equilibrium condition, when there is no change, when the delta yt, the lagged annual change of unemployment rate setting to 0, we have y low, which is mu1 minus alpha 1, and y high, which is mu1 plus mu2 by alpha 1 plus alpha 2, which is basically the maximum and the minimum of our y's, which correspond respectively to the low state where the weighing function is 0, and to high state where the weighing function is 1. Very simple, right? So first we have the equation and we have the weighing function. Indeed, the weighing function is the objective function, right? Or what should I say, the squash, the hidden layer, okay, in our artificial neural networks. Then it is represented in terms of error correction term, and we have y to present in two scenarios, in low state and in high state. In low state, the weighing function is 0. We don't have weighing function. Indeed, if we set weighing function to 0, we are only left with the low state. But if we set weighing function to 1, we have both of them present, right? And because this is taken on the left hand side, so we have the minus sign on top of both of them. The error correction parameters associated with these two equilibrium states, the error correction parameters are alpha 1 and alpha 1 plus alpha 2, as we already are seeing from this equation, which need to be negative to ensure that the low y are the negative, to ensure that the low and high multiple equilibria exist and satisfied the stability restriction. Beautiful. We have the negative sign, so to mention that we have a high equilibria and low equilibria, number one, and number two is that the model satisfied stability restriction, whereas the models alpha 1 plus alpha 2, which is the second equilibrium state, lies within minus 1 to 0. The results from estimating this L star model by maximizing the likelihood function is given in the next table for sample of t is equal to 734. The value of the likelihood function at the MLE is 0.16. The parameter estimates of the error correction parameters are negative, which is consistent with the present equilibrium, multiple present equilibria. So this is consistency testing. If our parameters are negative, we have well, our parameters are supposed to be negative, right? Because as our parameters are negative, we kind of have consistency with our multiple equilibria. The second error correction parameter estimate alpha 2 is statistically insignificant, suggesting the speed of adjustment, beautiful. This is insignificant, suggesting that the speed of adjustment to both low and high equilibria are the same and equal to alpha 1. So basically, because the first error correction parameter is quite significant compared to second error correction parameter is not very much significant, we know the speed of adjustment in both high and low equilibria will only correspond to the first equilibria, error correction parameter. So the speed of adjustment to both situations, low equilibria and high equilibria, are same first of all, and they are equal to the first error correction parameter. The point estimates also satisfy the stability restriction. So the estimate results are also located, the error correction parameter estimates are located within -1 to 0, the stability condition. So basically our results suggest quite a few stuff that we'll look for when we are going to do the application. First of all, is our error correction parameters negative? If they're negative, then they are consistent with the multiple equilibria, so consistency is satisfied. Then stability is satisfied, which is both of our error correction parameters are located between -1 to 0. Then we are going to look for which parameter is significant and which are not. Whatever is the significant parameters, for example in this case alpha 1, then we know the speed of adjustment for both the low and high equilibria points is basically alpha 1. Okay. Finally, the estimates to the low and high equilibria unemployment rates are respectively, from here we can estimate the low and high equilibria, and in case of low equilibria, these are the periods. If we go back to the figure, we see that these estimates of low equilibria and high equilibria kind of represent sensible estimates for the means of the different states of US rate, right? So we just need to prove this point, we just need to go back to the equation. I'm just gonna save this here. Okay. So I have just used L star threshold autoregressive model to solve for error correction models and to find speed of adjustment in nonlinear situation, and we can certainly go back to the previous figure to see the low and high equilibria, basically the maximum and minimum equilibria points. And in case of low equilibria, we know what our point is. In case of high equilibria, we know what our points are, and the mean of low and high equilibria kind of mean something to us. So aggregate unemployment rate are measured with the help of low and high equilibria, where the high equilibria are the peak points, low equilibria are the drop points, right? And that they make sense when we draw them. So wow, so L star and L star is logistic smooth transition autoregressive, because we do basically the TAR model is used with maximum likelihood estimation, so you know. Now okay, the next problem is bivariate threshold models of G7 countries. Anderson, Anthanasopoulos and Vahid investigate the relationship between the real output growth and interest rate spread of G7 countries using a range of nonlinear time series model. The variables are real output growth rate, again real output growth rate, and interest rate spread. Okay, these two are very important factors. This is the equation representation. We see simply a lag of real GDP and its lag. So where is our GDPT is real GDP, Y1T and Y2T. In case of Y2T, our 10-year and our 3-month T are respectively the 10-year and 3-month interest rates, both expressed in percentage. The sample periods vary for each country. Well, we take varying sample periods for each country, and these are Canada, France, Germany, Italy, Japan, UK, US. So G7 countries specifically, where output rate represented by the equation 1, interest rate spread is represented in equation 2. So log likelihood function values and residual covariance matrices of these G7 threshold models in the equations are estimated. So maximum likelihood estimation again. For each G7 country, a generic bivariate threshold model time is specified for each one. So a generic bivariate threshold model, where we have, you know, for the first equation we have the linear parameter, 2 lags, then the nonlinear parameter omega 1, and for the second equation, because it's a bivariate equation, nothing else, because it's a multivariate equation, so we represent it like that. So variable 1 equation 1, lag 1, variable 2 equation 1, lag 2, variable 1 equation 2, lag 1, variable 1 equation 2, lag 2. So this is both are same variable. Variable 1 equation 1 lag 1, variable 1 equation 1 lag 2, variable 2 equation 2 lag 1, variable 2 equation 2 lag 2, kind of like that. The disturbance vector and are distributed as I do 0 mean and V covariance, and the disturbance vector given, and we have each country's output and interest rate spreads, simulated TAR models of G7 countries based on maximum likelihood estimation. So given actual values, we simulate the TAR models. This gives us a very strong message. Wherever we take in one model, we simulate the nonlinear model, or we simulate the threshold models. Basically, that helps us to define the characteristics of the data that is given to us. The weighing function are, well, C is the threshold, right? And here lambdas are hiding the hiding the squashes, hiding the PR parameter inside. So the nonlinear model, the specification of the weighing function show that the adjustment between regimes in the rate of growth in output and interest rate spread are governed by lagged output growth. Other specifications, so lagged output growths are important, and they are governing the regular growth. So basically they're dependent on the lag, so or history. Other specification of the models can be entertained, including longer lag structure in each regime and alternative threshold specification. For example, in a next paper, they chose longer leg structure and threshold specification that vary for each country. They also delete parameter estimates that are statistically insignificant, like for the previous problem we had parameter 2, alpha 2, which was statistically insignificant. And the log likelihood function is as always, and we maximize the Newton-Raphson. The adjusted parameters in equations are fixed as, so the shocks are fixing at 100, which has effect of forcing the Elster model to become a Sitar model. Beautiful. One important thing finding from the research is that this particular threshold or a shock pushes the Elster model to become a Sitar model. So to explore the dynamic properties of the results, this figure is given in 19.11. Let's have a quick look at 19.11. Okay, oh, we have just seen this, right? 19.11. And what does this say? The dynamic of the simulated models vary across the countries. Canada tends to exhibit chaotic behavior with the dynamic of output and the spread characterized by a strange attractor. So chaotic behavior characterized by strange attractor. Why am I saying that? Very simple. Let's have a look. You have Canada output and you have Canada spread. You see it creates a region, but within a region it acts like a strange attractor. You see it becomes chaotic. It doesn't converge into the region, whereas Germany, Italy specifically, the region, everything else is converging on the outer band of the region. So this is not a strange attractor, this is becoming a limit cycle, but this is a strange attractor, right? Beautiful, very beautiful. So Germany and Italy converge to a fixed point limit cycles. France, Japan and United States converge to stable limit cycles, whereas the UK exhibit an unstable cycle. Okay, so that's what explains the cycles and the attractors that we studied earlier and how we can actually find them. So basically only a threshold L-star or Sitar model gives us these estimates, you know. Okay, so we'll look into this in further detail. The problem at hand currently is so we have done many of these problems, impulse responses and everything. So yep, non-parametric impulse response. So Elster model of unemployment, and the files are NLM US unemployment rate and Australian unemployment rate. We'll just have a look into just one problem. So NLM unemployment rate for US, let's see, let's bring it in here. In the meantime, just pause the recording so that time is not wasted in the recording. At this stage, this problem should not be difficult at all. So we're gonna start this problem. Mostly the data is given to us as we are estimating the unemployment rates, and that is in page 33, right? Let's go back to page 43. So we're gonna solve the unemployment rate problem here, and basically our data is given to us for many different periods of time. So we'll just gonna look into the solution of this problem, see how this problem is solved. First of all, we need to, in this case, in the unemployment rate problem, we need to estimate, we need to define log likelihood function. Okay, and because as you can see here, we need to estimate from this log likelihood function, we need to estimate quite a few parameters. And so you see, basically we have mu1, mu2, alpha1, alpha2. So quite a few parameters must be estimated for sample size of T734, and we'll take the error correction measure. So first of all, we need a wrapper function around, and we need to remember that we are gonna we're gonna use our data to develop our own data, and instead of minus mean, we do take minus sum, because here this is minus sum, not minus mean. So whatever the log function gives us, we need to take a minus sum of the logs, logistic function or the log likelihood function for two different error correction models. We're adding them up. So take minus sum p data, and p is our mu1, mu2, alpha1 and alpha2, as we remember. So you have p, and we have our data that we will pass in for the system to estimate a log likelihood function that we will maximize to estimate our parameters. So first, our first data is located in the first element, our lags is located in the second column, our standard deviations are located in the third column. Let's define the transition function. There might be a problem. This might be a mistake. I'm really sorry. This is not sum, because when I'm looking into the R function, this is the regular log likelihood function. That's why I was confused. This is mean. This is not sum. Just as before that we did, there's no change. We just have to find the concentrated log likelihood function at each observation. That's all. And because we are not doing any hypothesis testing, so unconcentrated is not required. So first column, second column, third column, as it is mentioned, transition function gamma. So gamma here in the transition function, gamma is this one, which is delta w by t minus 1. Very simple. So gamma is absolute value of the lag of p. So absolute value of the lag. Threshold is the end point. Threshold is the absolute value of the p is what we are estimating, for gamma, representing gamma. So threshold is the last element of that p. If this is p, in that case absolute value of the lag and absolute value of the last element, the final element, is threshold or C. So we have this equation now, which is ST minus C divided by S. So which is ST standard deviation minus threshold, ST minus threshold, or the third element here is minus threshold, divided by standard deviation. So ST minus threshold. You may ask why you are not taking gamma minus threshold, because we can't, because gamma is representing the whole element over there in the equation, the transition function, and the whole thing here, the whole unseen estimation that is happening here, because gamma is only associated with the first, with the numerator. It is not associated with the denominator, and the whole thing is ST, right? Whole thing is this equation. So ST minus threshold minus standard deviation of ST. So we're going to use raw data, the standard deviation ST. Then GT is the wrapper function. As we are done with this, now let's use this equation, and our GT is 1 divided by 1 plus exponential of gamma. Now gamma comes into play, multiplied to TMP. Okay. So we might make mistake in terms of transforming from the equation. We might make mistake in this particular element, which we should not. This is the standard deviation, not the threshold point. ST, the third element that the system will estimate here, the third parameter. Yes, third parameter is basically this one. Okay, so ST can be the seasonal, sorry, if this is yt minus 2, this might be yt minus 12, so the seasonal transition, not standard deviation. Delta 12 is the lagged annual change. S is the scaling factor equal to the sample standard deviation. S is the scaling factor, right? So this is the scaling factor and this is the sample change at 12 season. So S is the scaling factor that is equal to the sample standard deviation of these lagged annual change. Okay, now it's more clear. This is just the lag annual change. This is lag 2 and this is lag 12. Lag annual change, ST minus threshold. So there is nothing to remember. You can easily remember. And this is S scaling factor equals standard deviation of the lagged annual change. And then you have the transition function. Now let's compute the errors. Errors are mu1 plus mu2 y lag, mu3 plus mu4 y lag, right? And what are the errors? One more time. Well, you have from this equation, from the main equation, let's have a look into the main equation. So mu1 plus alpha 1 y lag, mu2 plus alpha 2 y lag. So error equals, the first error equals this, the second error in this equation equals this, right? And ut itself is simply y minus tmp1 plus tmp is itself, you take it here, y minus this parameter plus this parameter multiplied to the weighing function, gt, right? Very simple. That has been computed. So we have computed several things. First, we have determined the level, then we have determined the first lag, then we have determined the 12 lag, and the 12 lag is the unemployment change in unemployment rate, annual change in the unemployment rate. Then we define the transition function. We start with the stuff inside the bracket. So we defined which one the gamma is, we defined what the threshold is, and then we defined what the standard deviation of the scaling factor is, and we defined the transition equation. We defined the squasher, the equation inside, and using that we define the transition function. Now we have the transition function that we can use to specify the equation. So we represent the equation in terms of the residuals or the errors for the first element and for the second element. You know, so the first element is the first equation, and the second equation the two regimes. We represent the two regimes and complete our estimation with the completed GT. Concentrate sigma. So the sigma is simply standard deviation of the complete residual, and the log likelihood function is as it is. It has no change, u square divided by sigma square given u. Okay, and the system will return f and or return minus mean f would be easier to do. So let's go back to let's go to the main, equation. At this stage, I'm just gonna pause it. So first, I'm going to load the data. Then I'm gonna specify dating for plotting purpose so that I can plot against dates, which is beautiful to learn. Okay, and yeah, that is something I haven't learned before, and I'm excited to learn about that. So start date is starting from 1948. End date, date num is the function which transforms the number to date, this date to number. And x data is line space. We know linear spacing, where you give an interval against which the system automatically generates a vector with start date and end date. That it has done. A very simple function. Let's see how R do it. Well, R is very much familiar with sequencing, so it will do sequence as date. So we'll change these into as these numbers to date. So as date, that starts, you pass in the starting point and you specify how that will be represented in your rows. So you're doing it by month, and the length out is the line spacing here. Length out is 747. So you're saying that start as date, and by, you're saying that plot it by month. So take 30 days continuously and plot it by month, but in MATLAB I couldn't specify that. Length out is the line spacing. So length out, I repeat, length out is equal to linear spacing 747. So this is the asDate function. This is what the asDate, the sequence function, will give you. It will generate the system and then it will create the plot where we are plotting again unemployment rate against time. So unemployment rate against time, we are plotting the situation here. Data type linear, while between one unemployment rate x y against time. That's it actually. X data against our given data. So that's what we are plotting. We can fix this manually, however. And first we have that unemployment rate graph. Now we are gonna generate our do our estimation. So generate L star variable. First lag of y in the first period is level minus lag, and then the lag itself is the lag. Then 12th season is level minus lag. The lag itself is lag. So we have yt minus 1 and yt minus 12 that has been prepared for us, that we will be using. And then we adjust our data, see if they are not the same dimension, we'll make it same dimension. So dy is, because this has trimmed about 12 variables, so we'll just trim the 12 variables in both cases and then make them same dimension. Then we create our data matrix from here, okay, which is T is the total amount, that is corresponding to our length or the size of the Y observation. Let's do OLS first, which is once, and Y lag. Y lag, generally we put Y lag in excess, This is a good thing to do. We can always define the lag. We don't do this. This is not a practice. We generally put these inside and make things more complicated. Rather, we can always find delta and lag, define them beforehand, and that makes the codes much simpler and easier to understand. So we do YLAG, and we do a linear regression, which is LM in R is LM, dy linear regression on X -1, take the coefficient from that estimation, and the linear LR linear in case of linear is just minus bols 1 divided by bols 2, which is this one, right? Linear is when it is 0, the equilibrium condition is satisfied, that mu1 divided by alpha 1. Okay, we can create the elements for nonlinear model in this matter as well, and we can test with this code, size of x-lean, repeat matrix, regression, and blah blah blah, but let's not focus on that for now. We do optimization now. Okay, so our initial values are first dy, then YLAG, and the 12 lag. So these three inputs that we had is we are gonna use them for initializing our data. The three inputs we are gonna use. We have defined dy, you have defined YLAG, and we know dy as well. Dy 12 lag, we already defined them, and we have 6 parameters here, isn't it? And because we have 6 parameters, unknown parameters, 1 2 3 4, mu and variance, 6 parameters that we are gonna estimate from P. So basically that's all. Options optim set, we just call the function par. So we initialize P start, then par, then log L. So we did column bind, right? These are in columns or in rows. We did row bind here. Basically, when you say column bind, we are putting them in rows 1 2 3, in 1 2 3, yeah, we do column bind. So first one, second one, third one. Okay, good. I get always confused with this. And we run the optimization Hessian, and we have variance, covariance, and square root, everything. We just have we estimate everything now. Okay, all the parameters are estimated, and LR low, LR high, we know we solve for these two. That's all. So long run mean unemployment rate, LR linear, long run mean unemployment, LR low, and LR linear is simply this from OLS. In low state, in linear state is this, in low state and high state. So we estimated. So this problem is solved. Pretty easy problem, not much of a tweak in this. Then comes the next problem, which is bivariate L-star model for G7 countries, and we have seen this before we discussed this problem. Let's see if we can solve this problem, simulate the estimated models in L-star. So the problem is titled NLM-G7. So this was pretty easy, straightforward. US unemployment rate, and we can find the adjustment, speed of adjustment, and the significance test also gives us some important information. So we can derive quite a lot of information from this. Now we're gonna focus on NLM G7 and so you have NLM G7 opened. I'm gonna save this somewhere because this is a very important code we have been working on. Okay, let's just save it in another position. Okay, so NLM G7 and the G7 countries, we have local functions. We have several local functions here, right? And seems like a bit of difficult problem. However, it is an important one and probably the last one I'm gonna talk about. There is another problem, sunspot, but today we're not gonna discuss sunspots. Let's see though what sunspot talks about. So it's like a L-star model to find delay parameters. We can have a look. I think this one and the NLM one, this one and that one is the same thing. So first, unrestricted likelihood function. What do we have? We have number of observations, bivariate L-star model. Let's go up. Up, and we are here in our model discussion. We have different countries and different interest rates, and so we have B, number of observations, y1, y2, max lag. Okay, so this is what we are gonna find: y1, y2 parameters and maximum number of lag. So we are allowing our maximization to find out maximum number of lag for us, so that we know, because we're kind of trying to do what you know, what advancement has been done in this model later. Okay, so in 2007 longer lag structure were used by the authors of this model. So we're gonna allow the system to find this maximum lag for us. So for maximum lag plus 1 to number of observations, first we defined WT. What is W? The function. So W is being defined, or omega exponential 100 into the lag 100 exponential, then minus 100 scaled with 100, isn't it? Is that given somewhere? Just gonna jump around a little bit. Yeah, I know it's very irritating. Minus 100 yt minus 1 minus b11. Okay, yt minus 1 minus b11, yt minus 2 minus b22. So the parameters for residual and parameters for, you know, for all these equations, we do basically very simple thing here: y1 minus y1 minus what? Minus because we are representing this equation in this term. So the first b1, b2, b3, b4, b5 for the lag and then b6 and then this part. So we take, basically we are taking up 5 lags here, and then we are taking this b6, b7, b8, b9, b10. Did we miss the get data function? No, I think we'll come back. So there is another function, get data function. Okay, that is coming from the flag, but we'll talk about it later. Maximum number of lags. Okay. Unrestricted likelihood function, and then omega 2, and the residual we define that from, so the function first, the function, transition function, then the equation. So exclude the first, maximum lag, obviously we always do that to remove the initialization effect. And then VC for t is equal to 1 to number of observation minus the maximum lag, we do log likelihood function. So interesting, we're going backwards, number of observation minus the maximum lag. The log likelihood function and observation TE with n equal to, T is with n into the full likelihood function for sample of t is maximized, and estimating the model we adjust the parameter. This has never been discussed in the chapter, why we are doing y minus. So anyway, number of observation t minus yt minus 1. Okay, fine, I have no problem with that. Just something to memorize in this stage. I have no explanation. It's not currently being able to produce. So that's, we have the log likelihood function, then getting the data. Okay, and so we introduce something called flag. We have already done that so many times. strcmp, I'm not sure what strcmp is, I have never seen this. Okay, let me find it out. So here strcmp is string comparison. So you have two strings inside, maybe y, true and false. strcmp will compare true and false, and if they're equal, it will produce true. If they are not equal, it will produce false. So string compare true and true, result is true. String compare true and false, the result is 0, false, because true and false are not equal. Another example, string compare 1 and 2, a and b is false and b are not equal. String compare a and a are equal, so you get true. So let's initiate a if else if function. So if string compare, or here if flag equals 1, flag is Canada, then read Canadian data, where we are saying if flag equals 1, then read Canada data into y as matrix. We convert that as matrix. Else if France, we're gonna take any one data here. So that's why we're making this system so that we don't manually have to bring in data all the time. Germany, flag 4, every time you do in R, you see MATLAB by default reads the system in matrix, R does not. So read them as matrix, don't forget. And the function is called getData. We created that with the flag is the input, and we return the output. So that is so what did we do here? First of all, we defined the likelihood function, because for that likelihood function we needed the residuals and the transition function. We did that, and we also allowed the system to remove the first max lag observations, something to memorize. And we're getting the data now. Alright, then another function. So we have two functions now, getData function and log likelihood function. Compute the LM statistics to test for a bivariate term model assuming one lag in the auxiliary model. Now a testing function. So LM statistics, degrees of freedom, this will be returned to us. We'll input y, we'll import what DP, transition, and I-type. I-type is type of thing that we're gonna run. See, 1 2 3 4. I-type is regress yt, constant is ylag, and ylag squared. This is from very early reference to an equation that we studied in this chapter. If you can remember, ylag, then ylag. So this is ylag square, ylag, constant ylag on, ylag and ylag square. So it will go on ylag square, ylag cube. I-type regress 4, though it comes down, so ylag square is removed in the last I-type, right? This is, we referred in this chapter somewhere, there is an equation, but we're not gonna LM equation, we're not gonna go looking for it right now. Let's see though if we can find it here. So this is something we studied in page 726. You remember the augmented regression equation? See how the lags proceed, yt square, yt cube, but at the end they converge. So y square, right? Now you don't have the square, you just have the cube. So here is the same thing, square, right? Then I-type 3, cube is created. Then you take the cube only. In the third parameter you take the cube. So this is the augmented regression equation, auxiliary regression that we need when we are doing LM test, sampling LS properties of LST linearity test when we are doing linearity test. So that is for linearity test. And departure, how quickly the shocks should depart. So first stage regression, dependent variable, var and dependent variable, I'm really sorry. So first stage regression in LM, dependent variable, all rows up to dependent variable columns, 1 0. Then we take the lag. We could have defined it just like previous method in the beginning of this method, the earlier method here. Dependent variable, then the lag, then we do the regression and we find u, then we have z is dependent on transitional function, and z is choose the transition variable, which is lagged 1 period. Transition function or transition variable is taken. So if y-type equals 1, then we are gonna do what? Multiply with transition function. Z is 1. X all rows 2 to column, not the first one because the first one is x, then 2 to column. So z square, if else I-type is 2 in case of Canada, then you have every country's z square, z1, then z square, z1, z square, z cube. Transition variable, 0 rows 1 column, 0 rows 1 column. Okay, it will actually, the matrix will generate for all the countries continuously. If I type 4, okay, basing on I-type, right, lag squares, right, z cube and z square is coming up with z omega, it's coming up with omega. Oh, I-type, so omega pi or omega, let me check. Regress ut on yt minus 1, yt minus 2, compute the statistics. First, the regular regression. we got residual u, then we regress residual on all of these lags. Okay, fine, that explains that. So we do times so first we do z trim 0 1, just setting the dimension, taking the transition variable. Then I type 1 is z square, z squared, z1 z square. This is following, you know, z1 z square, regress ut on that. Basically this is following z here is Taylor expansion. See, z square, z cube, we are doing Taylor expansion. Okay, z square, z cube, so, and we are creating the matrix accordingly. Z square, so this is exactly as it is followed from this I types. Okay, then with all these regression we have residual at the end, whatever then LM statistics R square, and we know the LM statistics equation TR square and degrees of freedom. So this equation will build, it's quite difficult equation, but this equation will build LM statistics for us. Finally is the simulation, which we could have done that in the beginning, but let's just do it now. Y1 is zeros and initial value, beta simulation, number of observation, and this is exactly reciprocal. This is exactly reiterating the first one, the equation that we derived for log likelihood function, but we just exclude the first maximum log observations, and then we define log likelihood function. We used so many functions and for this estimation, and dependent is 1, transition is 2, transitional function is 2, nonlinearity test on GDP, so we are doing it on GDP now. So Taylor expansion, we use Taylor expansion, right? And let's go to 35. Transition is 2, and so we input the data to us, given to us, and first we get the data, get data function at any case, column bind all rows on column. So we are representing the country that we have collected in columns, and we are estimating its number of, we are getting prepared. Then perform bivariate LM nonlinearity test. So we just call for the in passing in the passing in dependent variable, a value for the dependent variable into initialize and transitional variable. We just call for the test for all those 4 I types. Okay, we're doing it for Y1. So LM statistics p-value, LM statistics p-value, LM statistics p-value. Okay, beautiful. Then perform bivariate and this on the spread. So dependent, now this time the dependent variable is 2. The second one, the second variable is the dependent variable, because we have growth rate and we have spread. Growth rate, the whole thing, transition happens twice, 2 lags. Spread, 2 lags. Again we run everything and then we optimize. Maximum of number of lag is 2 lags, as I said. Initial values, finally zeros, 22 rows, 7 columns. Okay, fine, no problem. Initializing, then optimizing, and then we have log likelihood function and covariance matrix. The final is now read in So we use we collect something from outside. I'm not sure what that is, so we're just gonna read the table and we're gonna simulate again this time. So we optimized our values, and with y start LF. We simulate value for Canada, we simulate value for France. We estimated the bivariate model here. Something important to remember, where we have B, bit, T, Y's, and maximum number of lags. We use our maximum number of lags. We use our final, which is 0, to initialize. We use y start. What is y start? Anyway, to understand this, we need to go back to the simulation. Y start. Okay, the simulation had y start, right? So starting value for y, maybe, yeah. Date, is it something to do with dates? No. Okay, fine. Starting value for y, final one, y start, y start, y start, y start. Okay, here, oh, starting values, simulate all models. So starting values, one rows, one column, that's all. So 2 columns actually here for GDP and for interest rate, and we estimate 2 different Canadian values. We simulate this stage, we simulate. And what are we gonna compare in all these cases? After simulation, we're gonna plot the result with our simulation, right? So we're gonna plot YLS Canada, YLS Canada. So the simulation, okay, Y1 is Canada, 1 to 100. We're just gonna draw a graph on the simulated results. France output, France spread. Okay, why did we optimize then? We simulated, we must have taken some optimized value for our simulation. Obviously we have taken max lag. What else? Obviously we have taken starting values, but that's not a big deal. Maximum number of lag is estimated for us. 100,000 estimations, fine, that's not a problem. Y start, then final. What was final? Final is something that is read from the final estimates. I need to have a look into final estimates. This system used Gauss estimates. Why Gauss estimates? We already estimated this thing because the question asks what did the question gave us and what did they didn't give. Estimate model by maximizing log likelihood function. We did that, right? Simulate each of the estimated models and discuss the dynamic properties of these models. All right, so we have estimated all the models from here, because you see, what are we estimating? We are estimating y1 and y2 fully for all the parameters, right? we're estimating our models and we have y1 and y2 fully presented to us. We're probably using these estimations to create a new simulation, right? Because we're using the first element of final. Because if you go back to beta simulation, B is the estimation results. Y start is nothing. So number of observations Y start. It takes y1, beta 1, y2, beta 2. So the estimation results are stored that we estimated. All the parameter estimation results are stored. Okay, we take the estimation results, we take 1, we take number of observations, it generates actually for generation, we take maximum, so maximum lag is estimated for us. Now it's clear. Y start is assumed, but beta is estimated for us. Number of observations is kind of like suggested by us, right? So beta sim takes all of these, right? This number of observations 100,000. All right, we are simulating the nonlinear models from our estimated result. Beautiful. This is the thing I have been talking to you from the very beginning, that what happens instead of using simulated data, if we are using observed data, we can take the observed data to estimate the parameters, and that the parameters we can take to draw our simulated nonlinear models, and the nonlinear models will capture the featured information of nonlinearity from given data. That is the exact example. Beautiful, beautiful, beautiful. It took me some time to understand because I'm looking in, I didn't deal with this code before. So big data, but it's much simpler, I think, in MATLAB, right, compared to R. It doesn't really matter, it's just plotting. The next function is just plotting, so not a big deal against each one, so that we know which one has the chaotic region and which one actually converges. Beautiful, it's very clear now. So 4 functions. What are the 4 functions? One more time. We need to do a likelihood function that we'll use for optimization. We need to create a function. We can create a function for getting the data from the, our table. This is a very good function. We can always do that. We need to create LM statistics, which is a bit difficult hypothesis for hypothesis testing purpose. However, this LM statistics for hypothesis testing is important because we are performing bivariate LM nonlinearity test to begin with. Okay, to see which are linear and which are nonlinear, which countries' data are linear, which countries' data are nonlinear. Though for our simulation or our model this is not important. However, we will only use this function to test for linearity and nonlinearity. And then we create a function for simulation that is exactly taken from log likelihood function specification. No change, right? There is one thing. Each time we take, just like while loop, each time our y's will increase by the number of initialization. Okay, y start. This is the use of y start. You can ask, what is the use of y start? This is going forward, moving forward, like p equals p plus 1 or c equals c plus 1 that we use our generally in while loop to restrict, to stop the rolling of the function. And the output actually remove the first max lag observation. So beautiful, 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 beautiful. And then sunspots, the data NLM sunspots. This is the final one. Let's open the NLM Sunspots one. Open. I'm not sure why this came up. NLM Sunspots. NLM Sunspots. You might be thinking that, well, I didn't compare the situation with R, the MATLAB code with R, how this thing is. It really doesn't matter at this stage. I mean, this is a magnificent program, and even if you have to download MATLAB for it, I would go for that. It's an easier program. The data Y are monthly average of daily sunspot numbers compiled by Solar Influence Data Analysis Center in Belgium. Sunspots are random generation of explosions in sun. Sunspots are magnetic regions on the sun with magnetic field strength thousands of times stronger than the Earth's magnetic field, whatever. They appear as dark spots on the surface of the sun and typically last for several days. They are first observed in 1600s. I really don't care. Plot the sunspot data and disguise the time series properties. Okay. Perform LST linearity test. Fine. Estimate. So we're gonna do our test again. Our testing, and then again the same thing that we did. I type and everything. Then L star model for sunspot by maximum likelihood estimation. Repeat for delay parameters. Now we have to find different delay parameters to see how that affects the results. Okay, so what are the functions that we are going to use? Beautiful. First, we're gonna create a function for hypothesis testing. Okay, LM statistic. First stage regression, you find residual. Second stage regression, you keep on the Taylor series expansion. You do Taylor series expansion. I think this is much easier in terms of, you know, in R. Let's compare with R now. Column bind. Present them in columns. Column bind. Present them in columns. Again, present them in columns is what column bind is. And no dots. Then LM statistics. R square, LM statistics, degrees of freedom. LM and degrees of freedom is simply size, number of columns of X minus K. Okay, X minus K, Y minus K, because how much have you, how many have you developed here? Number of columns of X minus number of columns of X. Degrees of freedom is number of columns of X minus number of columns of X. That can be 1, so in the first stage regression, whatever number column of X is we had, in the second stage regression have how much columns if we have extra data, extra data. Y bar. Okay, fine. This is the function, and the system will return here. It will list the LM statistics, LM and degrees of freedom, right? It will list. Okay, listed data. Then negative log likelihood function. Thank you. You presented in mean. So C, B12, B, Y, D, gamma, right? B and Y parameter, D delay function and gamma. In the question it is mentioned that I need D and I need gamma. So C is threshold, B12, and this is the transition function, Y6 minus DD, so exact representation of the transition function. List of variables in regime 1. These are all the variables in the first regime. List of variables in regime 2. These are the variables in regime 2 that must be given in the question 2, right? Delay parameter D2. So basically regime 1 is phi 1 yt minus I. So 6, 5, okay, fine, 4, 3, 2, 1. So 1 to 6 and 1 to 3. Okay, fine. So we'll take 3 and we'll take 6. That's all. Regime 1 has 6 variables, regime 2 has 3 variables. Very easy. Then you do the residual using the transition function, and then log likelihood function. Okay, fine, beautiful. This is the only 2 functions here in this problem. Great problem. Then we bring in sunspot data. We can just simply draw the sunspot data to see how it looks. Then we do linearity test. We just call for it, and we find p-value, which is 1 minus p chi-square, or 1 minus chi-square CDF, giving us the significance whether they are linear, or if our data is linear or not. That's all, nothing else. So we do it several times. Start test y2 3, all rows 1 column, length of. So we are doing the linearity test on different lags, right? Yeah. The delay parameter. Perform the linearity test on the sunspots data on enter and interpret. How many sunspots in sunspots daily sunspot numbers compiled by the monthly average of daily sunspot numbers. Ulster model of sunspots data. LST on data, right? LST on the sunspots data. Start test. Okay. Second stage regression. P equals 4. So we'll do it 4 times because P goes up to 4. Lag 4. Because lag goes up to 4. Right. In the question it says that we're gonna use 4 lags, up to 4 lags. Basically by default that is what we always do. Okay. By default in the second stage regression we always do this because it is what theoretically is supportive in all situations. It has nothing to do with lags or anything. So we do the linearity test 4 times, y3 and y4, y rows. So we'll do it y1, p equals 1, p equals 2, p equals 3, p equals 4. So we will do it several times. P equals 2, p equals 3, p equals 4 for all these p's, right? What is p? Have we been deciding on p? No, p is just we need to go back to understand this. We need to go back to LM. Control F. Okay. There is no reason to be, you know, not excited because this situation is currently very exciting. YT on. So basically this equation, what we are looking for is this equation, right? Assuming d equals p for simplicity, delay parameter. P is the delay parameter here, and by default the delay parameter we take up to 10, up to 4, 1, 2, 3 and 4. Delay parameter, if delay parameter is unknown, we assume d equals p and the regression is this. When the delay parameter is unknown, our specific situation does not know our delay parameter that we will estimate in the next situation. So as this is unknown, we'll continue our delay parameter with this. So now we find that delay parameter 2 is significant. Which delay parameter is significant? Okay, now this makes sense because we going to up to 4 steps. We try to find which delay parameter is significant, and we find 2 is the significant one. Gamma equals 1 is the adjustment parameter 1, 5, 10, 50, 100 given to us in the question, not estimated, again given to us. We can take 5, 10, 50, whatever. So and then we optimize, and because we have 11 parameters here, 11 parameters, because how many B and how many D you have and how many gamma you have, you just add them all up. Okay, and you just, you know, column bind 11 rows 1 column. C norm, this is optimization. Okay, theta naught, we optimize theta naught. with this delay parameter and gamma, right? Something like that. Okay, so we just estimate the parameters b, y, d, gamma, theta naught. Observe, oops, y10 and 11. Let's go back to our question. One, 5, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So we have quite a lot of stuff here. The problem is sometimes number of parameters gonna cause us problem. We gotta estimate quite a lot of parameters here. Unknown parameters are quite high, number of unknown parameters. For example, phi naught, phi 1, 1, 2. Okay, let's have a look. If we are just looking into autoregressive and these parameters, 3, 6 and 3, 9, 10, 11, 11 is the theta naught, first rows, and 10 beta, y, d, gamma. I'm not sure the 10 thing. Anyway, whatever the situation is, we're initializing our optimization from here. So these are initial optimization where we estimated delay parameter 2 is the best, and rows up to 11 rows. No, it's not row column thing. (11) and 10, okay, because lag, we are taking lag, that's why. First by 0.1s, then a specific number 10. Okay, this is not something, so then a specific number 10. I really am not sure. I need to look into it, do research on the data on the initial parameters, but let's initialize with this and we have our parameter estimates. Otherwise it's a very simple problem, very simple problem. We just need to know how many parameters we have. I wish they have mentioned the number of parameters we have. Estimate gamma conditional on 2. Okay, d2 is given. If gamma is conditional on 2, then gamma multiplied to d gives you 10, and you have 11 parameters here. That makes sense? Probably that makes sense, because we are repeat persist for alternative values for delay parameter d and use this result to derive MLE for d and gamma, because we are trying to find the MLE for d and gamma. I think that makes sense. Yeah, 9, 10, 11. So you have 11 parameters, multiplying them by 0.1. Basically you are initializing with that, and then finally at the end you have 10, the value of 10, that is for gamma, not for d. You are not estimating d. Okay, in this, oh, you are estimating d, right, I'm sorry. So b, y, beta, then y, then d and gamma. Okay, so these are initialized with this. Yeah, so the system will estimate b, y, d, gamma with initial value. D and gamma is given, b and y is what we are putting in. Y is number of observations or something like that, I'm not sure. I think this is gamma into 2, because this is not a this is something else in the early 1600s. This is not, you know, multivariate model, a single variate model. So thank you very much. We draw a line here and we conclude that this tan is d multiplied to lambda, d multiplied to gamma, and nothing else, and this is number of parameters. With that we will see what happens. Thank you very much.